Good afternoon, Shanika. Sorry, I'm having issues with the computer anyway.
Afternoon.
Let's see. I got all 5 of these. You ready to watch the daily quiz? All right. Gonna lock in 3, 2, and 1. Locking answers now. So the point of this property of isomorphisms was that identity elements map to
Identity.
by itself because it's a new group. Identity elements map to
The identity of the other.
identity of the other group. It's not mapped to itself. It can't necessarily, it does not necessarily have to be the same element. But it has to be the same type of elements, i.e. that it is an identity.
So suppose you say like EU and dash and cap.
Sure. Because mainly what I was caring about is making sure that you're knowing that it's mapping to an identity element. But also I know you can't necessarily do overline the keyboard, at least without a little bit of attack. So. All right, what questions do I got for me before we begin?
Oh, I have a question.
Yep, go for
It's not about math.
it. You might ask me after class then? All right, let's get the screen share up. So on Friday, thank you for telling me that. On Friday, we talked about 5 different properties of homomorphism and isomorphisms. And if it's a property for a homomorphism, then we can also a property for an isomorphism, right? Because isomorphisms are just bijective homomorphisms. So the first property was that identity elements map to other identity elements. Second one is that, if I raise a to some power, operate a with itself some amount of times for any positive integer, so including the case from operating the inverse of a with itself 10 times. It's the same thing as if I just mapped a through and then did that multiplication 10 times in the second group. Third group, third one, if 2 elements commute in the first group, then their images that they map to should also commute. That is what comes from an isomorphism. Because if the structure in the first group allowed for commutativity, isomorphisms are supposed to be preserving structure, then I would expect that structure to also hold in the second group. Third or fourth one, if group A is generated by physical elements, that's going to be true if you only have the other group that is isomorphic to it is also generated by the image of that element A. And what is the last one telling us?
The or the order cardinal
Order.
order of A is equal to the order of P of A.
Reserve the order too, right? Whatever the order of an element is in my group G, whenever I map it through the new group, which we're just calling G bar, it should have the same order, whatever that element is. And all of these properties, which we proved, lead into some other properties of isomorphisms on groups. So not just properties of isomorphisms themselves. We're not actually going to prove any of these in class, just because they all follow directly from that list of properties that we proved on Friday. So I'm going to let phi, going from G, E bar, in isomorphism. So it's just mapping from one group to the next. And that mapping is isomorphic. Well, an isomorphism is a what homomorphism? Bijective. And we can just go back to algebra and a little bit pre-calculus and say it's a bijective function. Then I also know the what of that function exists. The inverse of the function exists. And it turns out this isomorphism that we write, it's inverse because it will have an inverse because it is bijective, which is going from the group G bar to the group G. I'll just say it's isomorphism. I won't say as well. But its inverse mapping is also nice. Second, as a direct consequence of that commutativity property, saying that isomorphisms need to preserve commutativity of elements. We get that the domain G is abelian if only if the codomain. But also because of that first property that we just wrote out here, I don't have to look at it in just that perspective. I can flip it all around. If G bar is abelian, or if G bar will be abelian, if and only if G is abelian. Third one. Group G is cyclic if and only if G bar is cyclic. That's true if under the assumption that there is an isomorphism that exists between these two groups. Next one. If K is a subgroup of G, then its image. So if I take every element from the set K, that subgroup K, throw it through my mapping, that is also going to form a subgroup inside that second group G bar. Because its structure was that it was a subgroup, homomorphisms and isomorphisms preserve structure. So then it follows that its mapping, its image should also be a subgroup. And consequently, because of that first property, if I'm looking at a subgroup of that second group G bar, I'm just going to help to make sure we know where the subgroup's coming from. I'm doing K bar just to show that it's a subgroup of G bar. Then the inverse of P. So taking these elements from that subgroup A bar, well, what do you think that is going to become? Of what group? Not G inverse of G. G inverse is taking anything from G bar and mapping it into what group? G. So I'm taking elements from G bar, mapping it into G. And if K bar was already a subgroup, its structure should also be preserved. So I throw it through that isomorphism. It should also be a subgroup. And then one last one. Then it maps centers of groups to centers of groups. Again, preserving more structure. So I'm not going to do it in class, but each of these 6 items all just follow the properties of isomorphism. So what questions do y'all have? So for isomorphisms themselves, this is as deep as we're going to get into this particular topic. So we're going to switch gears a little bit. I'm going to take us back to a proof of Cayley's theorem. What was Cayley's theorem? What was it stating?
Every group is isomorphic to a permutation group.
Every group is isomorphic to a permutation group. And how did we create said permutation group?
You define it.
By what? Describe that process. How did we generate that permutation? Chris is doing that. That's good.
Ask the question.
How did we generate those permutations that made up the permutation group?
You found one that's isomorphic.
So we found an isomorphism between a group and the permutation group, but how did we define those permutations? Explicitly define those permutations of the group.
The one with P of G. I'll tell you, okay, so P of G is as G maps to G.
G doesn't map to G.
Bar.
So, okay, it maps from G to G bar. And then by what? How does it define that map? I take whatever my group element is I'm using, which is a little g, and multiply everything that gets thrown through it on the left by x. And we could define a similar mapping. Instead of multiplying on the left, we multiply on what side instead? The right. So if you play around with that concept enough, these permutations actually form a different type of structure. I don't have to make this a mapping. I can actually make this into a set. So a set created from left multiplication and a set created from right multiplication. And what we're going to call those are cosets. And cosets and what results from them, which is Lagrange's theorem, give us a lot of insight into what are the possible types of subgroups that I can have. Turns out that even though you can come up with the example, there is a pattern that will always appear. And you can always rely upon. But for us, we have to get there first. So I got to define something called a coset first. We're going to let G be a group. We're going to let H be a subset of G. So I'm not considering any structure on H. I'm not calling it a group. It's not a subgroup. It's just a subset, some collection of elements from group to group. And I want this to be non-empty. Essentially saying I do have things to work with. Then for any element in the group G, we are going to define two sets. The first is going to be what we call the left set. So little a times the subset capital H. And this is just going to consist of all elements. Saying, hey, take everything from this set H and multiply it on the left by this element that I chose, little a. And the other sets, or capital H with the little a on the right, is going to be similarly defined. But instead of multiplying everything in H on the left by A, I'm going to multiply everything in H on the right. Now here's the important thing. I can define these sets over anything, but they're going to be more particular, and I should have been more careful with using the term coset, because these will create what we call cosets, but only when that set H does actually form a subgroup of G. Okay. No, I'm not trying to skip anywhere. So when H is a subgroup of G, we call that little a times H the left coset of H in G containing A. We call HA the right coset of H and G containing A. So commonly we'll just shorten the term. You say right coset or left coset. What's up?
This is different than abelian, right?
Mhm.
Okay.
So you can start to see where some of this stuff can get interconnected. What's up, Melissa?
Here, you say when H in the,
Subgroup. Make that more sharp. So just an example to calculate cosets. So let the group that we're considering be the dihedral group of order 8, so all those symmetries on the square. We're going to let H, that set H, which is also a subgroup of G, be the set containing no rotation and rotating the corner of the square by 180 degrees. And we're going to just figure out what a bunch of these cosets look like. And one thing I'm going to do, I'm going to go back, I'm going to put this little curl on my H. That is just because we do have H reserved as one of the rotations for the symmetry of square. With the horizontal flip. That's just to help differentiate between that. set. I was looking at my lecture notes, I was like, why didn't I randomly switch to this like special H? Oh yeah, that's why. So we're gonna just go through and find all the left cosets for this set H. And just note that if I wanted to find all the right cosets, it'd be a very similar process. So to find this first left coset, R0, acting upon H. That means I'm going to take every element of H and operate it with R0, so no rotation. So what are the elements going to become? So technically, this is just the first time I'm going to write it out, maybe first couple times. But this is what all my elements will look like. I take every element in H, multiply on the left by R0. But I can reduce those down. I know what the outcomes are. And I think, Chris, you're already getting into it. I'm going to get that if I take R0 multiply on the left by every element of H, I'm just going to get H back. R0 and R1. This is my answer right here. If I look at the coset containing R90, well, this is R90 operated with R0, and R90 operated with R180. What will this reduce to? Mhm. Good. What about R180 acting on the left of every element of H? What are the elements going to be?
R180
Mm-hmm.
and R0.
Yep. What about R270 acting on this image? And I'm going to save us just a little bit of a headache. I'm going to just list out the others are because I don't want to make you go back to all your notes to find your Cayley table for the dimension group order 8. Remember, well, I can figure out what horizontal flip in R0 is, right? Because R0 is my what element for that group? Identity. So those are always going to be easy calculations, but then I have to remember horizontal flip with R1. Well, if I do that horizontal flip with R0, like we said, get your horizontal flip. If you do horizontal flip operated with R180, you get the outcome the same as doing a vertical flip. Then I go figure out what the left coset is when I have V acting upon H. So V composed with R0 is just going to be what? V. And when you compose V with R180, you're going to get H. And then my last two cosets are going to be my two diagonal flips, V and D. So, first question I have for you, will any of these cosets form a group? Will all cosets form a group? or a subgroup of D4, however you want to look at it.
Yeah.
Which ones?
First one. Third one.
First one, third one, that's it, and that's just because that left coset that came out was just my same one, or the same as mine. Yeah, my set H, which I know is a subgroup. The only time I was able to get a subgroup or a group coming out of these left cosets is whenever the coset came back to be the set itself. But I did notice some other things in there, right? If I took R0, its left coset, that was the same thing as the set H, which is the same thing as if I did R180, left coset. But that wasn't the only time I had cosets giving me the same outcome. What other cosets were the same? What other cosets have the same elements?
Has 0 and R1.
Oh, H and
So H and B, left coset want to use H, left coset want to use B. I'm just picking up on that one, I think that's the easy one for me to spot. I have to get you to clarify your statement, Carissa.
Then the next one would be the D and the H, and then the D prime of the H.
Yep, those two cosets were the same. And there was one more pair of cosets that are the same. You might have said it before.
I mean, R2 and R3.
Mhm. So what we see is that, okay, we're not necessarily creating more groups, but there's still some relationships there that can come out of these cosets. So it becomes an interesting question, at least, even if you don't know that there is a viable outcome for all of this study, in that we should probably figure out what are some more properties of subsets. Because if these two, or sorry, I said subset, cosets, because if these two cosets come out with the same thing, there might be a relationship between the horizontal foot and the vertical foot. There might be a relationship between R270 and R90. There might be a relationship between the two diagonal foots. So what is causing these cosets to be the same? Maybe depending upon what those elements are. So I'm going to write out a bunch of properties of cosets. My goal is to keep it kind of all on the left-hand side. And then on the right-hand side, I'm going to kind of write an interpretation of what these statements are actually saying. So for all these properties, we're going to let H be a subgroup of some group G. And we're going to let A and B, two elements A and B, come from that group G. First property is that whatever A is will always be in the left coset of H and G. Will always be in its own coset. Is that not what we solve for every single one of those in the dihedral group of order 8? R0 was in its coset, R180 was in its coset, vertical flip was in its coset, everything was in its coset. Second, A left coset of H will only be equal to that subgroup H. If and only if that element happens to be in that subgroup H. Third, we get some associativity with cosets.
Quick question,
Mm-hmm.
but if someone, does that mean like A is an identity?
Nope, it doesn't have to be an identity. So look back at. Let's see if I can keep it all in the same screen, but I can't. So H containing elements R0 and R180. I found the left coset of H with R0. And what set did it give me back? H, and same thing for R180. What set did it give me back? H, and this is because H is a subgroup. So if I take any two elements of H and operate it with themselves, what group am I going to still stay within? H. So it's really talking about closure.
So each got more than 2 elements.
H can have technically infinite order if we wanted to, or infinite number of elements. Actually, I'm not gonna go that crazy. I can be certain if I say it's finite, so if G is finite and H is finite, this will all hold. I believe it would also hold for infinite groups. Probably hold for integers and then like even integers. Maybe not all infinite groups, but it'll be some infinite groups. The third property is that we get this associativity of multiplication. So I can figure out whatever the element is that results in multiplying A and B and then generate the left coset of H. Or I could first get the left coset with B and then take whatever that set is and get its left coset to the element A. And this works whether or not you're working on right cosets or left cosets. Fourth property. These two cosets will be the same if and only if A is in the left coset of H from acting upon by B. Fifth property. States that these two cosets are either going to be the same or they have to be disjoint. If the two cosets are not the same, we're multiplying the left by A and the left by B, then they have to share no elements in up. Six. The left coset generated by A and left coset generated by B or containing A and containing B are equal if and only if the inverse of A times the element B in set H beginning or subgroup H. We've got three more. Seventh one, cardinalities are gonna be the same. Right, H has a defined number of elements. If I multiply everything on the left by A or B, I'm not changing the number of elements that are in there. I'm just changing what those elements look like. Eighth one. The left coset containing A is going to be equal to the right coset containing A. If and only if I can take all elements from H, multiply the left by A and the right by A's inverse, which gives the H back. And then last one. Also one that we already kind of noted. That left coset, which also consequently the right coset, will end up being a subgroup of G if and only if that element that you chose is coming from that subgroup H. Let's see how well I can put this in there. First one is just telling us the left cosets of H containing A does contain A. For me, second one, H absorbs the element A, if and only if, or absorbs the element, if and only if the element belongs to that subgroup H. Third property is just saying the left coset of H containing AB is the same as the left coset of BH containing A. Fourth one is any element of a left coset can be used to represent the coset. The coset was the H that I was initially considering. When I choose some element in there and then create a new coset, it'll have to be the same. It doesn't necessarily, it's not always unique, the labelings for any cosets. Fifth one. Two left cosets of H are either identical or disjoint. No in between. All elements have to be the same. or none of it. Sixth property gives us a way how to determine if two cosets are equal. All coming from elements of H. Seventh one, it's telling me that all left cosets have the same size. It did not matter what A and B were. It was any group elements, or whatever the cosets are that they create, have to be the same size. I'll admit, number 8, I don't have a great interpretation for. This is, I'm trying to remember where we use it. Fresh follow on this. This is one of those, it's like a weird property that is very useful in the proof on a major theorem. It is not necessarily something that is useful outside of it. At least as far as I can remember. But that last one is just saying H itself is the only coset of H that is a subgroup of G. And we're going to prove, I think all 9. Yeah. I think we can do it in the next 2.5 minutes.
You might as well not start it off.
No, but that'd be a waste of your money, time. Now, there's a couple of simple ones we can do. So, nice little same preamble, let H be a subgroup of G, group G. And let A and B be elements of that group G. We're going to prove the first one. That the left coset of H containing A does actually contain A. Well, since H is a subgroup of G, I know H contains what particular and important element? The identity elements. And since it's a subgroup, it has to contain that same identity element. Then the element A, I can think of really as just taking A and multiplying it on the left by the identity element E. Then has to be in what coset? Well, the coset where I took everything in H, multiplied on the left by A. Because it's an element of the set H. Yeah, this is just A multiplied on the left by an element in set H. So it must be in H. Or sorry, that left coset of H containing A. See, wasn't too bad. Let's see, last minute, let's just go back. I won't waste your time, but I'll go way over. I want to use that one, it's not because it's one proof, just because I like the top. But notice all of these cosets that we created. In the previous example. Every single coset had how many elements? Two sides. All cosets have the same number of elements. Anytime I created a coset with H where I used an element that was in there, we realized that the coset we got back was just the same thing as the set H. Let's see, another property we can go through real quick. That was the second one. So we realized we had an equality of all these different cosets, right? We had 4 different pairings that came up. But if I took the vertical shift coset for H, left coset for H, did that share any common elements with a diagonal shift coset with H? No. Right here, the elements in the coset with horizontal flip and vertical flip. Right here, those what 2 elements? The diagonal. Do they share any elements in common? No. If I go across second diagonal and let's just say the left coset of H containing R90, do they share any common elements? No, we can see all combination of these cosets are either the exact same or completely disjoint. And that disjoint property is going to be very big when I give us Lagrange's theorem. So we have class on Wednesday. No, holiday. When do we have next class? Friday. Okay. Look on Blackboard. You got 2 more homework assignments up there now after the one that's due today. There's one that is due this Friday, it just only deals with isomorphisms, isomorphism stuff. So start working on that, and there's another one that's due November 8th, I think. And that one involves some cosine stuff. So you'll have class Friday, next Monday, and next Wednesday before. And we're going to be talking about cosine stuff and how we get all the information for that. And I just wanted to put it on your radar. Want me to give you one homework assignments because at the end of the semester, your homework average is what percentage of your grade? Terrible students. You don't remember the syllabus? No.
What, 60?
No, less than 60. It was 50%. So how well you're doing on these determines half your grade overall. You want ample opportunities to prove to me that you can do this stuff. Okay. Plus, I prefer homework for this more than tests because homeworks you have more time to think about this stuff. If you have time, a less stressful environment, maybe you started this weekend, figure out what that isomorphism needs to be, right? Versus a 50-minute time block. Where you also have to do 3 other things to test, right? That's part of the reason why I put more emphasis on it. But there is going to be one more test. It will be in person, and we'll talk about that when we get closer to it. And the final is also going to be in person. Okay.
So what days is the second test in person?
I don't know when it's going to happen somewhere around Thanksgiving. Because we have the Wednesday before Thanksgiving, the 23rd, then we come back and we have Monday and Wednesday following it for classes, days of classes. So
I will.
why?
I won't be here.
Are you missing the final exam as well? What days are you gone? Oh, let me stop the recording so we can get on there.
Oh, you can scroll down.
Yeah, 1 sec.